what is NP hardness? So we have the SAT problem. We are given a SAT formula phi, and we are supposed to assign Boolean values to the variables and satisfy it. So given a formula, we want to know if there is an assignment that satisfies the formula. So when you think about this problem, you think about it for a couple of minutes, you don't see any solution, and then you are tempted to conjecture that this problem is indeed computationally hard. And indeed, we believe this to be true, but we have no proof. We are not even close to that. So what we do instead is we try to support this intuition that the SAT is supposed to be hard by showing that it captures hardness of some larger class of problems. And this is the class NP. So this is the famous Cook-Levin Theorem. It says that for every problem in NP, you can reduce it to a SAT problem. So if you are able to solve SAT efficiently, you will solve the entire class efficiently. So this sort of supports the intuition that SAT is supposed to be hard. But this also allows us to show that other problems are hard. So now that we have the notion of reductions from problems, we can start from SAT, reduce it to some other problem, and by that we can show that some other problems are also hard. However, this Cook-Levin theorem is fairly limited because it only allows you to talk about exact solutions. It only allows you to say if this formula is exactly satisfiable or not satisfiable. It could be very much close to satisfiable, but it still doesn't tell you anything about this. So a natural question is, what can we say about approximation? Can we say that also approximation is hard, or maybe it's easy? So this is, oh God. Yeah, so this is where the Pcp theorem comes into play. It says that approximation is also hard. So let's say it precisely. It says that there exists some constant less than 1, such that if I give you a SAT formula and I promise you that it's satisfiable, you are not able to find an assignment that satisfies C fraction of the clauses. And when you have this theorem, you can start proving hardness approximation results using, again, reductions. But this time, reductions are more difficult because you need to preserve the gap. You need to have a gap between satisfiable and far from satisfiable. But still, this is something that we can do, and people did it and studied it a lot. And by now, we have a lot of inapproximability results. So we know optimal hardness for 3SAT, for click. But for some other problems, such as max cut and vertex cover, we have some inapproximability result, which we suspect is not tight, but this is the best we know how to do. So I'd like to focus a little bit on this click result by Hastad. So let's see it. OK, so I'm not sure what's happening with the slides. It's supposed to come in slowly. But so here is the result of Hastad. It shows that if I give you a graph, and I promise to you that either it contains a click of size n to the 0.999, or it contains no click of size even n to the 0.001, it's NP hard for you to tell which one of these cases does your graph belong to. So if you are not able to distinguish between these two far cases, it means that this problem is hard to approximate. But let's consider this result in a picture. So in both cases, the click is actually small with comparison to the size of the graph. It's little of n. So although this gives us optimal hardness result, because approximating click within factor n is trivial. You just output one vertex. So this gives us a very strong result, but still it leaves something to be desired. You can still hope to get some stronger result. So can we get stronger result? Can we say that it's hard to find large clicks in graphs that even have clicks of size quarter, or maybe more? So let's see. So here is the most optimistic thing you can hope for. at least if you're trying to prove hardness. So suppose I will give you a graph, and I promise to you that it contains a clique of size half of the vertices. And I ask you, please find to me the largest clique you can. Then this looks like a very strong promise, so you say, OK, maybe I can find a clique that contains a quarter of the vertices. You think about it for a couple of minutes. You don't see how to do it. And we say, OK, maybe slightly less, maybe 1/16. But it still doesn't work. You still don't know how to do it. So how about anything non-negligible? How about a clique of size epsilon? So still, we don't know how to do it. And in fact, we suspect this is hard. We suspect that this task is NP-hard, but we don't know how to prove it. Even if we have this Pcp theorem and all of these techniques, we don't know how to prove it. And we need stronger assumptions. We need something called the Unique Induction conjecture that guys talked about, and I'll define next. OK, more slides issues. Yeah. So what is a unique game? So in a unique game, we have a set of variables x and a set of equations. Each equation is of the form xi minus xj is equal to b over some field, say over fq. So here is a particular instance of unique games. This is the max thread problem. So we have a graph. We want to partition the vertices into two parts so that as many edges cross this cut. So how do we formulate this as a unique game? So we simply introduce a Boolean variable for each vertex. And for each edge, we write down the equation that xu minus xv is equal to 1. This simply says that xu and xv are not equal. And then you see that this is a unique game. Good. So given a unique game, what is our goal? So the goal is to find an assignment that satisfies as many of the equations as possible. And this maximal fraction of equations that can be satisfied is called the value of the game. OK, so is everything clear? OK, so now that we know all of that, we can say what the unique game conjecture is. OK, so I'm really sorry for all of these slides issues, but I have no idea why that happens. So here is the unique games conjecture by Subhash Scott, made in 2002. It says that for every epsilon greater than 0, there exists some alphabet size q, such that if I give you a unique game instance over fq, it's NP-hard to tell whether you can almost satisfy all of the equations, meaning 1 minus epsilon, or at most epsilon of the equations. So at first sight, it seems like this problem is, maybe it's nice to study on its own, but why would it be helpful for anything else? But it turns out that it is. If you are willing to assume this conjecture, you can prove lots of hardness results. And the remarkable thing is that you can prove optimal hardness results for many, many problems. So optimal hardness for max cuts, for almost CSPs, for coloring, and so on. But there is a big issue here that this is a conjecture. This is not a theorem. So this is all conditional. So how about evidence? Do we believe this conjecture or do we not? So no one is really sure. There is no really consensus about this conjecture. And people worked on both directions. People try to prove some partial results, bring some candidate constructions that show that unique games may be hard. And other people, or maybe the same people, also try to design algorithms that maybe not run in polynomial time, but do something non-trivial. Yeah. So you think that this is the clicker? Mm-hmm. Yeah. So this talk is not really about unique games, but it's about something similar called 2-to-2 games. So again, we have variables, and we have equations. But equations now are of the form xi minus xj is either equal to b or to b prime. and again modulo q over some field. And again, we want to satisfy as many of these equations as possible. So again, in the same paper, Subhash conjecture that this problem is also hard. But here, you can hope for hardness for perfect completeness. You can hope that this problem is hard to distinguish between satisfiable instances and epsilon satisfiable instances. And to be honest, up until recently, we believe this conjecture maybe to be of equal difficulty. We knew nothing to prove about both of them. But recently, we managed to show something about this conjecture. So this is a sequence of work with Subhash Kot, with Irit Dinur, Guy Kindler, and Muli Safra. So we managed to almost show this conjecture, except that we have this imperfect completeness. So, okay, some bugs from Guy's talk. So we managed to show that this problem is hard, but between 1 minus epsilon and epsilon. And this gives you some evidence for the unique conjecture. So it's fairly easy to see, we'll have the proof on this slide, that given this theorem, you can show that unique games between half and epsilon is an NP-hard. So this is sort of the first result that's showing that unique games between some constant and epsilon is hard. And as I said, the proof for this is really one line. So how do you do that? So you want to reduce equations of the form xi minus xj equal b or b prime to unique equations. So how do you do that? You split them, right? You split them into two equations, and you call it a reduction, and you add a little dot to indicate that this is a proof. Yeah, but apparently this makes a difference. Yeah. So for the rest of the talk, I'd like to tell you a little bit about the theorem, what goes into the proof, and so on. But before that, let's discuss, again, the unique games conjecture and discuss algorithms and hardness for it. Okay, so let me tell you some implications of this new theorem of the hardness of 2-to-2 games. So as I said, we have the result for 2-to-2 games itself, and we have the implication for unique games. Then we have hardness for some combinatorial problems. So we have hardness for the clique problem that we started this talk with, which is equivalent to some vertex cover between some different numbers. We have hardness for something close to a coloring problem, and then we have something for max cut. And finally, we have this very interesting conjecture made by Boaz Barak called the Intermediate Esp Conjecture. So this conjecture so I'll set it as a theorem because it's a theorem now. Assuming the exponential time hypothesis, never mind what's that, there are constants alpha and less than beta, and a natural CSP, unique games itself, that has an algorithm running in time 2 to the n to the beta, but has no algorithm that runs in time 2 to the n to the alpha. So it says that the actual complexity of unique games between half and 1% is something weird. It's not 2 to the n, it's not polynomial, it's some 2 to the n to the alpha, where alpha is some number. So this was not known previously. So there are probably more hardness results you can prove using this new 2-to-2 result. We didn't try too hard because we think that it's interesting by its own, but this is something that may be interesting to do. So I'd like to tell you a little bit about unique games and some of the history of works that went into it. So this is the slide of where I tell you about algorithms and hardness for unique games. So it all started with the paper of Kot, where he suggested this conjecture, and he also did some sanity check. He tried the best algorithm techniques that there were then, SDP algorithms, and he showed something that they can achieve. But of course, they didn't refute the conjecture, otherwise he wouldn't publish it. And then other people tried to refine these SDP algorithms and their analysis, but still nothing refuted it. But still, the question was maybe there exists some analysis that everybody missed that refutes the Unique Induction conjecture. But then the hardness side strikes, where they show that these SDP algorithms cannot work because here is one graph on which they fail. So this is a paper by Subhash Kot and Vishnoi. They show that SDP algorithms cannot work. So now it's back to algorithms people to show some evidence that maybe UGC is false. So then a large family of unique games were shown to be easy. These are unique games on expander graphs, and they capture a lot of natural unique game instances. So for example, maybe you would hope that if you take a unique games instance at random, maybe this is hard. But what this tells you is that this is actually easy, because if you take a random graph, it's an expander. So it means that hard instances do not look random. They have some structure to them. So then there were these partial results. So O'Donnell and Wright show that unique games between half and 3/8 is NP-hard. And then there was another paper by Kot and Moskovich that showed that some candidate construction for hard unique game, but it's candidate. It's, they have no proof for the soundness, and it's not actually for unique games, but for something weaker, but never mind. And there is this sub-exponential time algorithm by Aurora, Bark, and Stower, and by Stower. So this algorithm is very interesting. It shows that you can solve unique games better than trivially. You can run in 2 to the n to the epsilon time and distinguish between the yes case and the no case. So prior to that, the best that was known was just try all the assignments and see what fits. But this algorithm gives you something better. And there was some hope that maybe you can just improve the analysis of this algorithm, and it would by itself show that unique games is false. But one consequence of the recent line of work is that this cannot be the case. So recently we've shown that unique games between half and little of 1 is hard. And these algorithms, the sub-exponential time algorithms, they work equally well if you feed them a unique games instance with value 99% or with value half. So what they're really trying to do is they're trying to solve now a task that is provably NP-hard. So of course you will not be able to analyze them better unless you believe that P is equal to NP. But yeah, so this you can view it as strong evidence for unique games. But if you still don't believe UGC, then at the very least you need to come up with new algorithmic techniques, because all the algorithms that we currently have no chance of working. So let's get back to this slide, and let me finish this first part of the talk with the problem that we started with, the clique problem. Then again, we have this graph. I promised you that it contains a large clique, maybe not half of the vertices, something more modest, 29% of them. But now I can prove to you that it's NP-hard to find the clique of size epsilon n. You no longer need an assumption about something that is not proved. Okay, so any questions? Okay. So in the rest of the talk, I'd like to tell you some ideas that go into the proof. Of course, I'll not manage to say everything, but at least I hope to tell you one new thing. So it's still buggy, Muli. Yeah. So how do you prove a Pcp theorem? How do you prove inapproximability results? So you have to start with some problem, free start or something like that, but then you have to compose it with something called an inner PCP. And if you want to isolate only working on an inner PCP, this is something purely coding theoretic. So an inner PCP is an error-correcting code C, along with a randomized local test, T. And this test has to satisfy the following two properties. if you run this test on an actual code word C, then the test always accepts. So this is called the completeness, and the soundness of the test is sort of an inverse type property. You want the following property. If you have some word W, W is not a code word, but you know that running the test on W accepts with non-negligible probability delta. Then you want that whenever this happens, it means that W is close to some code word in C. Okay, so this is the two very basic properties that we want from our inner PCP, and this is called the local to global phenomena because this test is local. It looks at maybe 2 or 3 places in the code word, but still, if you know that this test passes with non-negligible probability, you get some global structure on W. You get that it's close to a code word. So let's be a little more concrete. So what does it mean to be close to a code word? So usually it means that they are just close in Hamming distance. That, or maybe close is not the right word, they are correlated in Hamming distance. They agree on at least epsilon fraction of their coordinates. And when you think about this simple sense, this actually is something that has a name in coding theory. This is locally decodable code and list decoding. And there are many examples. So starting with the work of Blum, Luby, and Rubelfeld, Sudan, Ras Safra, Aurora Sudan, and Hastad. For us, we'll actually need a less simple sense. We don't really use the Hamming distance, but let's keep that for later. Yeah. So let's give a simple example. So this is the BLR linearity test. So I need to tell you what is the code and what is the test. So the code is the following. You consider all linear functions from 0, 1 to the n to 0, 1. And for each linear function, you have a code word. This code word is simply the truth table of the function. So you go over all inputs, and for each one of them, you write down a bit, indicating what is the value of the function on that input. So this is known as the Hadamard code. I hope that you have all seen it at some point. So what is the test? So the test is very simple. So if you have a linear function, you expect that f of x plus y would be equal to f of x plus f of y. This is the definition of what a linear function is. So what you do is you really test this property. You take 2 inputs, x and y, randomly and independently, and you check whether f of x plus y is equal to f of x plus f of y. So you read 3 locations from the word. For the location x plus y, for x and plus y, you make this test, and if it holds, you accept. So what can you say about this test? So first of all, this test has perfect completeness. If f is an actual code word, if f is a linear function, then whatever x and y you choose, this equality is going to hold. And the more interesting question, usually in these things, is the soundness. So suppose I tell you that here is some f that passes this test with slightly larger than half probability, say half plus delta. Then the soundness says that any such function is correlated with a linear function. Yeah. So this is a very canonical example. So how does it relate to hardness? So suppose I want to prove hardness for some problem A. How do I choose my code and my test? So it turns out that if you want to prove hardness for problem A, say linear equations, your test T should use linear equations. This is the connection between hardness and testing. And because the BLR test, you can view it as a linear equation in 3 variables, you can use it to prove hardness for equation modulo 2 using 3 variables. And this is, again, the result of Hastad. So if we want to prove some hardness for 2-to-2 games, we need to come up with a code and a test that uses 2-to-2 checks. And this is what we'll do in the rest of this talk. So I'll just add that this code that we are going to see is still talking about linear functions. It's something linear, and this is really important. OK. So here is maybe the most important object in this talk. This is called the Glassman Graph. So we have some linear space V over F2, and we denote its dimension by k. And we have a parameter L, which is much smaller than k. Then the vertices of the graph are all of the L-dimensional subspaces of V. And two vertices, L and L prime, are connected by an edge. Well, so they can intersect on dimension at most L, and it has to be an integer. So whenever they are very close, whenever they intersect in dimension L minus 1, we connect them by an edge. So this is the graph. So next, I'll describe to you what is the code that we're using, what is the Gasman Coder, what is the test, and what all of this has to do with expansion. So let's define the Gasman code. So for every linear function from the vector space V to F2, we have a code word, just like in the Hadamard code. Except that now we don't write down the truth table of the function. We write down all restrictions of the function to subspaces. So for every subspace L, we write down the restriction of little f to L. And then we line up all of these restrictions, and this is the code word. Okay, so let's say it again. For each subspace, we have a coordinate, and we write down in this coordinate the restriction of f to the subspace. So let's discuss some parameters of codes just to get a feeling for this code. So let's fix one subspace. So how many bits do we need to specify a linear function on L dimensions? Well, it's over F2. So we just need to specify for a basis what is the value. So there are 2 to L options for that. So this is the alphabet size of the code. What about the length? So for each subspace, we have a coordinate. So the length of the code is the number of subspaces that there are. And this is roughly 2 to the L times the dimension of V. So maybe one last thing. What about the distance of the code? So if you have two linear functions that are distinct, and you randomly choose a point, then the probability they agree on a point is half, because this is over F2. And what this means that is if you choose now a larger subspace, if you choose maybe L independent vectors, then the probability they agree is 2 to the minus L. So what this tells you is that the distance of the code is fairly large. It's close to 1. OK, so now that we know what the code is, I can tell you about the test. So the test is very simple. So what you do is you sample an edge, LL prime, uniformly from a graph. And then you read the symbol that is in the coordinate of L, and you read down the symbol for L prime. So this is two linear functions. So you check whether these linear functions agree on the intersection of the subspaces. So this is the picture. We have the subspace L and the subspace L prime, and we check whether the two symbols agree on the intersection. So now I need to convince you about many things. First, I need to tell you why this test a 2-to-2 test. And then I need to tell you that it is complete and sound. It will not be so simple, but let's start slow. Let's say that this is a 2-2 test. So the reason is as follows. So let's look at the intersection L intersection L prime. So this has dimension L minus 1. And for whatever linear function we have on the intersection, there are exactly 2 extensions of it to L and 2 extensions to L prime. Linear extensions, because there is only one more dimension, and you can assign it either value 0 or 1. So this is why this is a 2-2 test. So what about completeness and soundness? So it's easy to see that this test is complete, because if these symbols are indeed some restrictions of some global linear function, then of course they agree on the intersection. It's the same function. So it passes with probability 1. And the trick question is about the soundness of the test. So suppose I have some assignment G that passes at least epsilon fraction of the test. Well, you should think of epsilon as a small constant, say 1%. What does this information give me about this G? Does it mean that G is close to some code word in the Gasman code? So this question is actually not so simple, at least in the sense that the way I stated it, the answer is no. You don't have to be correlated with a linear function or with a code word, an actual code word. So we need to be a little more careful here about what we state. But still, there are some senses in which you can study this question. So let me recap this first part of the talk. So we've established, in the sense that I told you that there is a reduction from an NP-hard problem to 2-2 games. And we discussed hardness for unique games, for click and vertex cover. We concluded that the thing that has to be studied is the soundness of the Glassman test. So again, I have this assignment that passes with at least epsilon probability in the test, and I want to conclude some information about the structure of the assignment. So in the rest of my talk, I'd like to tell you about this question and about how we study it using expansion. So I'll not actually relate the 2 questions. I'll just tell you about expansion. So in this sense, you can, if you lost me so far, you can try to hop back in. But it turns out that this is really the key thing that you need to study. So are there any questions? OK. So let's talk about expansion. So here is a quick definition of what expansion is. So suppose we have some deregular graph G. So for a set of vertices S, we define the expansion of S to be the following probability. We pick a vertex from S uniformly at random. Then we pick a random neighbor of it, L prime. And we ask, what is the probability that L prime is outside the set? In other words, what is the probability to escape the set in one step? So usually when we say a graph is an expander, what we mean is that for all sets of size at most half of the vertices, their expansion is bounded away from 0. The probability to escape them is at least 1%. This is what an expander usually means. But for us, we will not near perfect expansion. We want that the expansion of any set, at least for small sets, is close to 1, is at least 1 minus epsilon. So the first question is, what can we say about the Gasman graph? So here is a fact. If you have a set S that contains delta fraction of the vertices in the Gasman graph, its expansion is at most 1 minus delta. So there is a limit to how close to 1 you can be. And the question is this a true limit? Meaning, is this an equality, essentially? or other sets for which it is much smaller. So it turns out that there are sets for which this is much smaller. And I'm going to give you them in two flavors. So the first kind of sets, we call them zoom-in sets. And they are defined as follows. So you take X, a non-zero vector, and you take all of the L-dimensional subspaces that contain X. Then I need to tell you that this is, first of all, a small set. And secondly, that it has small expansion. So why is this small? So because X is one vector out of 2 to the k vectors that are in the universe, and because L is much smaller, the probability that if you pick a random L, it will contain X is smaller. So this is the reason this set is small. And secondly, this set has expansion roughly half. So this is you can see it in the following way. So let's fix one vertex inside this set. And let's take a random neighbor. Then the question is, what is the probability that this random neighbor would also contain X? So let's look at the picture. So we are asking, what is the probability that X is a common vector to L and to its neighbor? But the intersection between L and its neighbor is of dimension L minus 1. So half of the vectors of L are in common with L prime. So this is the probability. This is the reason the probability that X is one of the common vectors is half, at least roughly. So this gives you already one set of examples that show that in general there is no equality. It could be much smaller than 1 minus delta. But actually it gets worse. There are more examples. So I'll do it in less detail. This is called a zoom out example. So now instead of taking a point, you take a hyperplane. And you consider all L-dimensional subspaces that are contained inside this hyperplane. Then you can see, I'll not do it, that this set is both small and has expansion roughly half. So what is going on here? Are there any more examples? Do we need to make a third bullet? Or is it all that the Gasman graph has? Let's make two observations about these two examples. So these examples are in fact very natural. Both of them, if you look at it carefully, are by themselves Gasman graphs, but of smaller order. So in the second example, what you did is, instead of looking at the entire V, you look at only W. So this is, you made the large space smaller. In the first space, what you did essentially is, instead of having L-dimensional subspaces, you fixed one dimension, so you have L minus 1 dimensions. So I'm saying things a little vaguely, but you can make it precise. So are there any other examples that are not Gasman graphs of sets that do not expand well? So certainly one thing that you can do is make combinations of these sets, meaning you can take intersections and take unions, and these sets will also be not so good expanding. So for example, here, what we did is we took a bunch of points, x1 to xq, a bunch of hyperplanes, and we intersected all of the previous examples for x's and w's. And this is just a small technical term. I refer to the number of restrictions, the number of x's that we fixed in hyperplanes. I refer to it as the co-order of the graph. This is just the number of restrictions that we made. So obviously, the previous two examples are one case of this, where the intersection is just one element. So these previous two examples are of co-order 1, because we only fixed one dimension, and they are non-expanding. The expansion is half. And in fact, in general, you can show that as long as you take not too many intersections of these examples, these examples are small, and also have expansion bounded away from 1. And what we're after here is a converse type theorem. We want to say that this essentially is all you can do. Meaning, if you have a set S that has expansion bounded away from 1, then it must be one of these sets. This is obviously false, because you can take unions. So what you want to say is that any set that has expansion bounded away from 1 is correlated with one of these sets. And this is precisely this question. So this is the statement that we'd like to prove, that if a set has small expansion, then it is correlated with one of these examples. So remember that we used to talk about PCPs and 2-to-2 games and all of these things. And we got to this math question. And the question is, why should we bother about it? So I'll not tell you the reason, but the issue is that we realize that if you want to analyze the soundness of the Glassman test, you really have to study this question first. If you are not able to prove this, then you have no hope of analyzing the test. So this is we thought about it as a first step that may lead to a proof one day in 20 years. But then it turns out that by Barak, Othar, and Stower, that all you really need to do is resolve this question. And actually, it's not even that hard. It's very elegant and beautiful. So if you want to prove now something about PCP, about 2-to-2 games, it all reduces to this extremely mathematical combinatorial question about sets in the Glassman graph that have no expansion. So this is what we're after. We're after proving the theorem. So what can we say about this statement? So the short answer is that it's true. The longer answer is that it takes some time. So what can we say about it? So this is just a counterpositive of the statement. It says that if you have a set S that has no correlation with these examples, its expansion must be close to 1. Just took the negation of the previous statement. So we suggested this statement along with some partial results together with Dinur, Kindler, Kot, and Safra. So we managed to show that if S has no correlation with co-order 1 examples, whatever that means, then you've passed the 1/2 barrier. Your expansion is at least 3/4 minus a little bit. So this already tells you that in some sense, all examples of expansion half are what we saw. But again, what we really want is get close to 1. So can we do something about that? So in the same paper, we did something more than that. We proved that if you have stronger assumption of no correlation with co-order 2, then you can guarantee a larger expansion. You can show that expansion is at least 7/8 minus a little bit. But this is already harder. So the previous result is very clean and very nice. I could tell you the proof if I had time. This is already not so elegant, because you need to do some case analysis, and it gets messy. And actually, the higher you hope to get your expansion, the messier it gets. So this is like a point that we stopped. We weren't sure about how to proceed. But then we learned about this Barak-Othari-Stower paper, and we realized that this is all you need to do. So we had some more energy, and we did that. So we proved at the end that if you assume no correlation with co-order R, then your expansion is at least 1 minus 2 to the R. This is a paper with Kot and Safra. So this essentially said that the statement, as we stated, it is true. And thereby you get all of the results about 2-to-2 games and all of that. So I want to say maybe 2 words about the proof. It's uses Fourier analysis. And Fourier analysis is, in its basic form, says that if you have a Boolean real-valued function over the hypercube, then you can represent it as linear combination of monomials. And this is very useful to prove a lot of things, but if you want to do Fourier analysis on the Gasman graph, it gets more complicated because you don't have product structure and you don't have this basis monomial, and things get more messy. So you need to get your hand dirty, or maybe work with a different graph that still is related. So maybe I'll say one more word here. So those of you that are aware of things like Bonaby-Bechdel equality, also called the hypercontractive inequality, this is very much in the spirit of that. But you need some extensions of these theorems to other domains and with tighter parameters. So let me conclude the talk. So we've seen the theorem in the last, in this part. We saw that if you have, on the Glassman graph, you have no correlations with a constant coorder, which is called pseudo-randomness, but never mind, then you get near perfect expansion. At the first part of the talk, we discussed implications about 2-to-2 games, unique games, and some combinatorial problems. And the question is, what about the future? So we can hope for a lot. So this Gasman graph business is something that is new in the TCS community. So one can hope that it will lead to further developments. I can already tell you that something that are more math-related, such as subthreshold phenomena and things like that, have been done using tools from here. But we can still hope for more things in TCS, maybe even the Unique Induction conjecture, but this is still wide open, and we don't know how to do it. And with that, I'll end my talk, and thank you very much.